Hey guys, this is a quick video just to go over graphs of motion. So we'll look at graphs of constant velocity and graphs of constant acceleration. So the first thing we need to look at before we look at either of those is no motion, which is pretty boring but important. So we'll look at velocity equals 0. So along the bottom, that's our motion chart. Every time the car moves, I'll make a new dot. Along the right-hand side, I've got the position x charted against the time, and we'll see how that changes as I progress time. So each time the car moves, I'll put a new dot. After 1 second, the car hasn't moved, so it stays at x equals 1, which is where it started. After another second, yes, nothing has happened. A third second, still nothing has happened. You get the idea. The car always stays at x equals 1. It's never moved along the bottom. So this looks like x of t equals 1. It's pretty boring. Next thing is constant velocity. So here we actually get to move. And let's just say the velocity is 2 meters per second. So every second, I'm going to move the car 2 meters. So it starts at the first dash, that's x equals 1. After 1 second, it's at 3 meters. After 2 seconds, it's at 5 meters, then 7, then 9, then 11. You get the idea. If you take a look at these dots, it looks like a straight line. And if we wanted to put an equation to that straight line, we'd look at y equals mx plus b, which is the equation of a line. We get something that looks like this. X of t equals 2t plus 1. Notice that red 2 is the same as the red 2 over on the left, and that is not a coincidence. In general, the position can be written in terms of the speed. So x of t equals vt plus x naught, and x naught just means wherever you started. In this case, we started at 1, so that's why that thing is a 1. So that's constant velocity. Next thing to look at is constant acceleration. Now, here, our speed is going to change, and acceleration is a measure of how that speed changes. So if I said the acceleration was 2 meters per second, or 2 meters per second squared, it means every second, my speed will increase by 2 meters per second. So just to give you an example, let's say that I start with v naught equals 1 meter per second. So when I start my clock, I'm moving at 1 meter per second. Well, 1 second later, I will be moving at 3 meters per second. And notice, since I was moving at 1 meter per second before, over the first second, I traveled 1 meter. Now, though, I'm going 3 meters per second. So if I go another second, I should go 3 meters. And indeed, I go 3 meters. But now my velocity is 5 meters per second because I'm still accelerating. So now I should go 5 meters in the next second. And if you take a look at the graph, you see that it is definitely not a straight line. This looks something like a polynomial, maybe a parabola. But we got a little problem here, and the more astute amongst you will probably have recognized that if I'm accelerating the whole time, then somewhere in the first second between going 1 meter per second and 3 meters per second, I'm probably going 2 meters per second. And I didn't really take that into account when I graphed my position. So I guess a good way to look at this would be to break it up into smaller time chunks. And then we can say every half second we'll see what happens. So I start just as I did before at x equals 1 with a speed of 1. After half a second, now I have a speed of 2, and I've gone half a meter. After 2 seconds, after 1 second, I now have a speed of 3 meters per second, and I've gone a little further. And we're doing the same thing we did last time. You can see now the red dots, they're actually a little higher than they were before. I'm moving farther than I thought I was. Of course, this doesn't really solve our problem because maybe I should be looking at quarter seconds or 8 seconds or 16ths of a second. I will never get perfect by doing it this way. So we need another solution, and that unfortunately means we need to do a little bit of math. Our position at any given moment is going to be given by our initial position plus our average speed times however much time goes by. Basically, I look at where I start, I look at on average how fast I'm going and how much time has gone by, and that'll tell me where I am. But our average speed is just our final speed plus our initial speed divided by 2. I get to do that because the acceleration's constant. And if I do a little bit more algebra, I remember that the speed is acceleration times time plus v naught, algebra, algebra, algebra. This is the thing that's important. X of t equals x naught plus v initial t plus 1/2 at squared. This is indeed the graph of a parabola. So, in summary, in general, motion has a graph that looks like a parabola when you have constant acceleration. If the acceleration happens to be 0, the parabola turns into a straight line. And if the speed happens to be 0, it's just a flat line, which is boring. Anyway, I hope this has helped.